this video, we're going to be talking about subsets, and we're going to be revisiting set theory. Okay, so suppose we look at the set A equals 1, 2, 3, 4, 5. And I'm actually going to write that out here. A equals 1, 2, 3, 4, 5. How many subsets of A contain exactly 3 elements? First, a simpler question. How many subsets of A are there total? In other words, what is the size of the power set of A? Well, we're trying to find the cardinality of the power set of A. Think about how we would build a subset in general. We need to decide for each of the elements of A whether or not to include the element in our subset. So we need to decide yes or no for the first element, yes or no for the second element, and so on. And so for each choice we make, we need to decide yes or no for element 2 and so forth. For each of the 5 elements, we have 2 choices. Therefore, the number of subsets is simply 2 times 2 times 2 times 2 times 2 by the multiplicative principle. Of those 32 subsets, how many have 3 elements? Well, this is not obvious. Note that we cannot just use the multiplicative principle. Maybe we want to say we have 2 choices, yes or no, for the first element, 2 choices for the second, 2 choices for the third, and then only 1 choice for the other 2. Well, but what if we say no to one of the first 3 elements? Then we'd have 2 choices for the fourth element, and this is a terrible way of approaching the problem. Here's another bad idea, though. We need to pick 3 elements to be in our subset. There are 5 elements to choose from, so there are 5 choices for the first element. And for each of those choices, there are 4 choices for the second, and then 3 choices for the third. The multiplicative principle would say then there are a total of 5 times 4 times 3 choices, which is 60 ways to select 3 element subsets. But the power set, but the size of the power set, which is the total number of subsets of A, is 32. How can it be that of those 32 subsets, 60 of them are size 3? No, that's not possible. So none of these ways are accurate. They're not logical, they're not valid, because 60 is greater than 2. One of the outcomes we would get from these choices would be the set 3 to 5. So let's explain why this is wrong here. Of these 60 choices, one choice would be 3 to 5. By choosing the element 3 first, then the element 2, then the element 5. Another outcome would be 5 to 3. By choosing the element 5 first, then the element 2, then the element 3. But these are the same set. We're double counting sets here, obviously, at least. We can correct this by dividing, because many of the sets of these 60 sets here, we're double counting. We're counting multiple times. For each set of 3 elements, there are 6 outcomes counted among our 60, because we can arrange this in 6 different ways. We could do 3 to 5, 5 to 3, 3, 5, 2. We could do 5, 3, 2. We could do 2, 3, 5. And we can do 2, 5, 3. And so in this group of 60 subsets, we're counting each set 6 times. So since there are 3 choices for which element we list first, 2 for which we list second, and 1 for which we list last, we expect there to be 10 3-element subsets of A. So it shouldn't be 60, it should be 10, which is 60 divided by 6. Each set in here, each different set is counted 6 times. It's not double counting, it's 6 counting. I don't know if that's a thing. Well, we could list out all 10 of these different subsets, being very systematic in doing so to make sure we don't miss any or list any twice. Or we could try to count how many subsets of A don't have 3 elements in them. How many have no elements? Well, just 1, which is the empty set. How many have 5? Well, again, just 1. These are the cases in which we say no to all of the elements or yes to all of the elements. Okay, what about the subsets which contain a single element? Well, there are 5 of these. So let's go through this real quick. We're counting all the different sets here. Again, the size of the power set of A we said was 32. Now, let's talk about subsets that are size 1 or size 0. We said there are only 1 of them, which is the empty set. And then the subsets that have size 5 are, well, there's only 1 of them. It's the whole set, A. You can't find any other subset that's also size 5 that's actually different. Size 1. Well, that's if we pick, again, 1 element from set A. There's 5 ways of doing that. Now, what about all the subsets of size 4? How many of those are there? Well, picking a set with a subset with 4 elements is the same as basically saying that we're rejecting one of the elements. How many ways can we reject one element? Again, that's like saying this is like saying no to exactly 1 element. Well, we can do that 5 different ways as well. Now, we're just missing size 3 and size 2. Well, so far we have counted 12 of the 32 subsets. We have not yet counted the subsets with cardinality 2 and with cardinality 3. There are a total of 20 subsets left to split up between these 2 groups. But the number of each must be the same. If we say yes to exactly 2 elements, that can be accomplished in exactly the same number of ways as the number of ways we can say no to exactly 2 elements. So the number of 2-element subsets is equal to the number of 3-element subsets. Together, there are 20 of these subsets, so 10 each. And that's another way we can show the number of subsets of size 3. Anyways, thank you so much, and I'll see you in the next lecture.